Welcome to Lesson 2.1 Prerequisites Verification. Before we write a single line of fine-tuning code, we need to confirm that every layer of your stack, Python, CUDA, PyTorch, and your GPUs, is correctly installed and talking to each other. Catching a misconfiguration here saves hours of cryptic errors later. Learning objectives. This image shows the completed prerequisites checklist. Every item marked with a green OK. Python 3.11.14, NVIDIA SSMI detecting both Tesla P40S in TCC mode, CUDA 12.1 driver, PyTorch 2.0 or higher with the CUDA suffix, right single. Both GPUs detected 24 gigabytes of VRAM per card. The GPU computation test passing, and both transformers and accelerate installed at the right versions. This is the target state. If your environment matches every line on this list, you're ready to install Onslaught. This diagram shows the full software stack you're building on. At the top is your code, whether that's a Python script or a Jupyter notebook. Below that sits the training layer, Onslaught and the Hugging Face TRL and PF libraries. Under that is PyTorch 2, 6.0, which handles tensor operations and automatic differentiation. PyTorch talks to the CUDA stack, the runtime QDNN for optimized neural network primitives, and NCCL for multi-GPU communication. All of that runs on NVIDIA driver 539.xx for Windows. And at the very bottom is your hardware. 2 Tesla P40 GPUs with 48 gigabytes of VRAM combined. Every layer in this diagram needs to be correctly installed and compatible with the layers above and below it. That's exactly what this lesson verified. This table shows the hardware requirements alongside your actual specs. The minimum GPU VRAM is 8 gigabytes. You have 48 gigabytes across 2 cards, which is 6 times the minimum. The minimum CUDA version is 11.8. You have 12.4. The minimum driver version is 520. You have 539. Python requires 3.10 through 3.12. The 2 items worth double checking on your own machine are RAM and storage. The recommendation is 16 gigabytes of system RAM and 50 gigabytes of free disk space. Models and datasets take up more room than you'd expect. Make sure you have that headroom before the next lesson. By the end of this lesson, you'll have personally verified 5 things: that Python 3.10 or later is installed and on your path, that your CUDA driver is in place, that NVIDIA SSMI sees both of your Tesla P40S, that PyTorch can actually reach your GPUs, and that you have the full 24 gigabytes of VRAM available on each card. Every check builds confidence that the foundation is solid before we install anything on top of it. Step 1. Check Python version. Vernser doso, versions doso komau, Chopins, Fasti, Sin Mins, Mitet Shokasi, Dromikwika. The command here is simply Python Bardensor version. What you're looking for in the output is a version number in the 3.10, 3.11, or 3.12 range. 3.11 is the sweet spot for this course. If you see 3.9 or older, the latest versions of packages like transformers and Onslaught won't install cleanly. If you see 3.13 or newer, you'll hit the opposite problem. Package support hasn't caught up yet. The ideal output looks like Python March 11th 14. That's exactly what we want. If Python version fails, try Python 3 version on some Windows setups. The 2 commands point to different things. The companion command where Python is equally useful. It prints every path on your system where a Python executable lives. If you see multiple paths, that's a sign you have several Python installations competing with each other, and the one that runs when you type Python might not be the one you expect. Knowing exactly which interpreter is active is the first step to fixing any version mismatch. Step 2. Verify CUDA installation. This compatibility matrix shows which CUDA versions work with which driver versions, and it explains a subtlety worth understanding. Your driver version is 539. That driver fully supports CUDA 11.8, 12.1, and 12.2. CUDA 12.4 is marked as partial, meaning the driver can run PyTorch builds targeting 1.2.4, but you may hit edge cases with certain operations. The safest target for this course is CUDA 12.1 or 12.2, both of which are fully supported by your current driver. If you want full CUDA 12.4 support, you'd need to upgrade to driver 550 or higher. For our purposes, 539 with CUDA 12.1 is the reliable choice. This is the NVIDIA SMI output for your specific setup. 2 rows, 1 per Tesla P40, driver version 539.42, CUDA version 12.2, both GPUs showing 0 MB used out of 24576 MB total and 0% utilized. The mode column reads TCC for both cards. Every number here is exactly what you want to see. The TCC mode confirmation is particularly important. That's what enables these server-class GPUs to function as pure compute devices on Windows rather than display adapters. The NVCC output confirms the CUDA toolkit installation. The key line reads release 1.2.1, V12, 1.66 inches, toolkit version 1.2.1, build December 1st, 66. This is the CUDA compiler version. Distinct. Having the toolkit at 12.1 means your PyTorch CUDA 12.1 builds will have everything they need. This output, combined with the NVIDIA SMI confirmation, means both the driver layer and the toolkit layer are correctly installed. NVIDIA SMI is your first real hardware handshake. This utility talks directly to the NVIDIA driver and reports back everything the driver knows about your GPUs. Run it now and you'll see a table with 1 row per GPU. The two numbers to focus on immediately are driver version and CUDA version. These appear in the top right corner of the output. You need driver version 520 or higher because that's the threshold where CUDA 12x support was introduced. The CUDA version shown here is the maximum version your driver can support, not necessarily the toolkit version you have installed. That distinction matters and we'll come back to it. Here's what a healthy NVIDIA SMI output looks like for your setup. You should see 2 rows, one for each Tesla P40. Each row shows the GPU's bus ID, temperature, power draw, and memory usage. Right now, both cards should show 0 MB used out of 24576 MB total because nothing is running yet. That 24576 MB figure is the number to confirm it corresponds to exactly 24 GB per card. Also notice the mode column. It should read TCC, not WDDM. TCC mode is what allows these server-class GPUs to be used for compute workloads on Windows without a display attached. If you see WDDM, the GPU is being treated as a display adapter and PyTorch won't be able to use it efficiently. NVCC version checks something different from NVIDIA SMI, where NVIDIA SMI reports what the driver supports. NVCC is the actual CUDA compiler. It's part of the CUDA toolkit package. The output will show you a release version like release 1.2.1, V12 1.6. That 12.1 is the toolkit version. For this course, CUDA 12.1 or 12.2 is the target. If NVCC isn't found at all, don't panic. For most users, the driver alone is sufficient because PyTorch ships with its own bundled CUDA runtime. You only need the full CUDA toolkit installed if you're compiling custom CUDA extensions from source. The NVCC output is straightforward but worth reading carefully. The line that matters is the one starting with release. in this case release 12.1, v12 1.66, that confirms the CUDA toolkit version installed on your machine. The build number after the V is less important. What you care about is that the major version is 12 and the minor version is 1 or 2. If you see 11.8, pytorch will still work, but you'll need to use an older build. If you see 10.x, that's too old for any of the current tooling. Step 3. Verify PyTorch installation. Once you offer these techniques quickly, this terminal output shows the PyTorch version check result. The version string reads 2.6.0 plus cu124, PyTorch 2.6.0, compiled against CUDA 12.4. The next line returns true, confirming CUDA is available. The final value is 2, confirming both GPUs. Notice the CUDA suffix here is Q124 rather than Q121. That's fine. PyTorch 2.6 with CUDA 12.4 support will work correctly with your driver. The version string format is what matters. Any Q12X suffix confirms GPU support is active. This flowchart maps out the CUDA verification process as a decision tree. Start with NVIDIA-MI. If the GPU isn't detected, install or update your NVIDIA driver. That's the root of the tree. If the GPU is detected, run nvcc -version. If CUDA isn't found, the toolkit isn't on your path. If CUDA is found, check whether PyTorch can access it with torch.cuda.is available. If that returns false, PyTorch needs to be reinstalled with a CUDA-enabled build. If it returns true, you've reached the end of the tree. Your environment is ready for training. Follow this sequence in order. Each step depends on the one before it. This one-liner, python-c import torch print.torch versions all is the fastest way to confirm PyTorch is installed and importable. The version string it prints carries critical information. A string like 2.5.1 plus q121 tells you three things at once. The PyTorch version is 2.5.1, it was compiled against CUDA 12.1, and GPU support is included. If the suffix reads plus CPU instead of plus cu121 or plus cu124, you have the CPU only build. It will run, but it won't touch your GPUs, and fine-tuning will be impossibly slow. The suffix is the thing to check. Now we go one level deeper. This command asks PyTorch three questions in a single line. Is CUDA available? How many GPUs can you see, and what are their names? The first answer, write single quote torch.cuda.is_available ASCII, is a hard gate. If it returns false, nothing else matters until you fix it. If it returns true, PyTorch has successfully initialized the CUDA runtime and can schedule work on your GPUs. The device count should be 2, and the names should both read Tesla P40. If you see only one GPU or a different name, that's a signal to check your driver and TCC mode settings before going any further. Here's what the combined output looks like when everything is working. The first line shows your PyTorch version with the CUDA suffix, confirming GPU support is compiled in. The second line reads true, CUDA is available. The third value is 2. Both GPUs are visible to PyTorch. If your screen shows this exact pattern, your deep learning framework is fully operational. Any deviation from this, false, 0 GPUs, or a CPU-only version string, is a clear diagnostic pointing you to the right fix. If PyTorch is showing a plus CPU suffix, here's the fix. First, uninstall the existing CPU-only build with pipe uninstall torch.torch audio. Then reinstall with the CUDA-enabled version by pointing pip at NVIDIA's dedicated index URL, pip install torch audio index URL https://down. That index URL is the key. It's what routes pip to the CUDA 12.1 builds instead of the default CPU-only packages on PyPI. After the reinstall, run the version check again and confirm the +CU121 suffix is present. After reinstalling, run python massc import torch print torch CUDA as available CC one more time as a final confirmation. This single line cuts through everything and gives you a definitive true or false. True means your GPU is reachable and you're ready to move forward. False means something in the installation chain still needs attention. Driver, CUDA version, or the PyTorch build itself. Step 4. Check GPU memory. You'll master these techniques quickly. This screenshot shows the GPU memory check output. 2 Tesla P40s, 24 GB each, 0 allocated, 0 reserved, full VRAM available. 2 GPUs means you can leverage parallel training strategies that would be impossible on a single card. That 48 GB total VRAM figure is what makes this hardware genuinely capable for fine-tuning large models. You have room to work with models and batch sizes that would immediately run out of memory on consumer GPUs. This table is a quick reference guide for the most common setup problems. CPU-only PyTorch. Reinstall using the CUDA index URL. Wrong Python version. Create a new virtual environment with PyBishu 3, Bishu 11, Bishu M. GPU not detected. Check TCC mode with NVIDIA-ME-DM0. CUDA version mismatch. Reinstall PyTorch targeting the CUDA version that matches your driver. Each of these fixes is targeted and specific. None of them require reinstalling your entire system. If you hit any of these issues, this table tells you exactly which command resolves it. This Python snippet iterates over every GPU PyTorch can see and prints 4 memory figures for each one. Total memory, currently allocated memory, reserved memory, and free memory. The reason we check all 4, not just total, is that PyTorch maintains its own memory allocator that reserves blocks from the OS and then manages them internally. A GPU can show reserved memory even when your code isn't actively using it, because PyTorch is holding that allocation for reuse. Right now, before any training has run, you want to see allocated and reserved both at 0 and free memory close to the full 24 GB. The output you're looking for shows 2 GPU entries, each reporting a total of 24.00 GB. Both allocated and reserved should read 0.00 GB at this point, and available should be the full 24.00 GB or very close to it, accounting for a small amount the driver reserves for itself. If you see gigabytes already consumed and nothing is running, a previous Python process didn't release its GPU memory cleanly. The fix is straightforward. Restart your terminal or run NVIDIA shme-dshcp reset if the memory stays locked. A clean baseline here means you'll have the full 48 GB across both cards available when training starts. This screenshot confirms exactly what we want to see. Both Tesla P40s are listed, each with 24 GB total VRAM, and the memory is completely unallocated. 2 GPUs with 24 GB each gives you 48 GB of total VRAM, enough to fine-tune models that would be completely out of reach on consumer hardware. That headroom is what makes your setup genuinely powerful for this work. Step 5. Test basic GPU operations. This is the GPU computation test output. Both Tesla P40s detected, 24 GB each confirmed. Matrix multiplication completed in 0.0034 seconds. That's not a typo. That's 3.4 milliseconds for a 10,000 by 10,000. The memory bandwidth check returned OK. All tests passed. This result proves your GPUs aren't just detected, they're executing compute operations at full speed. That's the final confirmation you need before moving on to installation. This is the final prerequisite check output, the complete picture, Python 3.11.14, pytorch with CUDA support, 2 Tesla P40s with 24 gigabytes each, transformers and unsloth at their required versions, and the closing line, all prerequisites satisfied. This output is your green light. Everything from the Python interpreter down to the GPU hardware has been verified programmatically. You're not hoping the environment is correct. You've confirmed it. The next lesson builds directly on this foundation. This script does something more meaningful than just checking flags. It actually puts your GPU to work. It allocates two 10,000 by 10,000 matrices on the GPU and multiplies them together, then measures how long it took. Matrix multiplication at this scale is essentially the same operation that dominates transformer training. So this is a realistic stress test. The script also reports memory usage before and after, then cleans up by deleting the tensors and calling write single quote torch.cuda.empty_cache cursor to return that. If the computation completes without errors and the result tensor shows device CUDA 0, your GPU is not just detected, it's actually computing. The output tells you everything you need to know in a few lines. The device line confirms which GPU handled the work. The time, around 0.23 seconds for a 10,000 by 10,000 matrix multiply, confirms the GPU is operating at normal speed. The result shape of 0.00010000 confirms the computation completed correctly. And the memory usage figure, typically under 1 GB for this operation, confirms there are no memory leaks. If this takes longer than 5 seconds, the computation may have fallen back to CPU, or there's a driver issue slowing the PCIe transfer. A clean, fast result here means your GPU is ready for real training workloads. This screenshot shows the full test output. Both GPUs are listed with their 24 GB of VRAM confirmed, the matrix multiplication completed in milliseconds, and the memory bandwidth check returned OK. Every line of this output is a green light. If your screen looks like this, you have a fully functional dual GPU compute environment ready for fine-tuning. Step 6. Check Python packages. You learn these techniques quickly. Full analysis and practice. You'll master these techniques quickly. This command pipes piplist through FineStr to filter for the 3 core packages torch, transformers, and accelerate. The /i flag makes the match case insensitive. What you're confirming here is not just that these packages are installed, but that their version numbers meet the minimums. You need torch 2.0 or higher, transformers 4.30 or higher, and accelerate 0.20 or higher. If any of these are missing from the output entirely, they're not installed. If the version numbers are too low, you'll need to upgrade before proceeding. If transformers or accelerate are missing, one command covers both. Pip install transformers accelerate. Transformers is the package that provides model architectures, tokenizers, and the training infrastructure that Unsloth builds on top of. Accelerate is what handles the complexity of distributing work across multiple GPUs and different hardware configurations. It's the layer that makes multi-GPU training feel seamless. After installation, rerun the pipe list check to confirm both packages appear with their version numbers. Prerequisites checklist. This is what a fully passing prerequisites check looks like. Python March 11th 14 confirmed. PyTorch with CUDA support confirmed. 2 Tesla P40s, each with 24 gigabytes confirmed. The transformers and accelerate libraries at the right versions confirmed. The final line reads, all prerequisites satisfied, and that's the only line that matters at this stage. If your output matches this, you're not guessing that your environment is ready. You know it is. Every box checked means you're standing on solid ground. The next lesson is where things get interesting. Unsloth installation. Common issues and solutions. If write single quote torch.coda. Is underscore available Ace Air Care returns false? That single line is telling you one of three things. PyTorch was installed without CUDA support, your GPU driver is too old to be recognized, or there's a version mismatch between the CUDA runtime PyTorch expects and what's actually on your system. The fix depends on which of those three is the cause, and the next few commands help you figure out which one you're dealing with. Start by checking the PyTorch version string. Run python-c import torch print torch.so version and look at the suffix. If it ends in +CPU, that's your answer. The CPU only build is installed. The fix is a two-step reinstall. First, uninstall with pip uninstall torch-audio, then reinstall with the CUDA index URL pointing to the Q121 builds. After the reinstall, run write single quote torch.cuda.is_available arca again. If it now returns, if NVIDIA SMI shows significant VRAM already consumed and nothing is running, a previous process didn't release its GPU memory. The command NVIDIA SMI does GPU reset attempts to force reset the GPU. If that doesn't clear it, a full system reboot will. The GPU memory is completely flushed on restart. This situation is more common than you'd expect during development, especially if a Jupyter kernel crashed mid-training. Getting into the habit of checking memory usage before starting a new run will save you from mysterious out-of-memory errors. If your terminal responds to Python with something like Python is not recognized as an internal or external command, Python isn't on your system path. This doesn't necessarily mean Python isn't installed. It means Windows can't find it when you type that command. The first thing to try is searching your start menu for Python to confirm it's installed at all. If it is installed, you need to add its directory to your path environment variable. Open System Properties, navigate to Environment Variables, find the path entry under System Variables, and add both the Python installation directory and its script subdirectory. On Windows, the Python launcher gives you a clean way to target a specific version, Py-3.11 version. If that works, but Python version doesn't, the launcher is installed, but Python isn't on your path. The path fix involves two entries. The directory where python.exe lives, typically something like sisu users your name abda local programs python tokens, Python 311, and the script subdirectory inside it, which is where pipe and other. Add both. Open a new terminal window and the Python command should resolve correctly. If pip is installing packages to the wrong Python, or if you're seeing import errors for packages you know you installed, the cleanest solution is a virtual environment. The command pe-3.11-mvm creates an isolated Python 3.11 environment in a folder called VM. Activate it with python vm v scripts activate and your prompt will change to show the environment name and From that point on, every pip install goes into that isolated environment, and every Python command uses exactly the Python 3.11 interpreter you specified. No more version confusion, no more packages installing to the wrong place. If write single quote torch.cuda.de vice_count echoes returns 1 instead of 2, one of your GPUs isn't being seen by PyTorch. The most common cause on Windows is that one card is in WDDM mode rather than TCC mode. Run NVIDIA SMI and check the mode column for both GPUs. The one showing WDDM is the one PyTorch can't use for compute. Switching it to TCC mode requires running NVIDIA -my-dm1-i from an elevated command prompt, and we covered that process in the environment setup lesson. When a GPU isn't showing up, NVIDIA SMI is your first diagnostic. Run it and count the rows in the GPU table. If you see only one Tesla P40, open Device Manager with Windows + X and look under Display Adapters. Both cards should appear there. If one is missing entirely, It's a hardware or slot issue. If it appears in Device Manager but not in NVIDIA SMI, the driver may not have initialized it correctly. Try a driver reinstall. If it appears in NVIDIA SMI but not in PyTorch, that's the TCC versus WDDM mode issue described above. Final verification script. Vanis herbosis ostus odronstes teredis. Vanis verification script. Rather than running each check individually, this script consolidates everything into one pass. It checks your Python version against the 3.10 minimum, verifies PyTorch is installed and reports its CUDA suffix, calls write single quote torch.cuda.is underscore available Tanaba, counts your GPUs, and then checks for transformers, accelerate, and datasets. Each check prints. The value of running this as a single script is that you get a complete picture at once. If 3 checks pass and 1 fails, you know exactly where to focus. If all checks pass, the script prints a confirmation that you're clear to proceed with Unsloth installation. Running python verify underscore prerequisites.py write single quote gives you the definitive readout. Watch for the Python version line first. March 11th 14 is what you want to see, then the PyTorch line with its CUDA suffix, then the CUDA available true confirmation, then both GPUs listed by name, then the package versions. If datasets isn't installed yet, that's fine. Unsloth will pull it in as a dependency when we install it in the next lesson. Every other check should show a pass before you move forward. Key takeaways. Here's what this lesson established. Python must be in the 3.10 to 3.12 range. 3.11 is the recommended version. Your CUDA driver needs to be version 520 or higher to support the CUDA 12. X runtime. PyTorch must have a CUDA suffix in its version string plus CPU means you need to reinstall. Both Tesla P40S must be visible to PyTorch with TCC mode active and 24 GB of VRAM each showing as available. And the GPU computation test must complete in under a second. Every one of these checks has a clear fix if it fails, and you now know what each one is. Next lesson, your prerequisites are verified and your environment is confirmed solid. In lesson 2.2, you'll install Unsloth itself, including the Windows-specific workarounds for Flash Attention and Triton, which don't have native Windows builds. That lesson is where the fine-tuning stack becomes complete. See you there.